All right, I'm ready. Questions from this assignment? Colette. 7. It says to find the magnitude and direction of the vector. Find your angle, degrees, rounded to the 100th. Okay? So the magnitude shouldn't be too bad. I'm just going to use the magnitude formula. Okay with that? Okay. To find the direction, I'm going to begin by drawing a picture. So if I draw this vector, I go 3 over and 4 down. So the vector is somewhere over here. Now the direction that I'm looking for is this. Okay with that? That's the direction. So what I'm going to do is I'm going to make a reference triangle. That angle on the reference triangle there that forms with the terminal side and the x-axis I'm going to refer to as alpha. And the side lengths of this triangle are 3 and 4 because I've gone 3 over and then 4 down. So alpha is going to be then tan inverse of opposite over adjacent. And when I type this into my calculator, I get approximately, I don't know, it's like 53 something, I think. Yeah, 5313. And I'm going to then use that to find the value for theta. So what's the relationship between theta and alpha? Theta is 360 minus alpha. So that means it is 306.87. So my magnitude and then my direction. Is that okay there, Colette? Yeah. Okay. So again, got to make sure you're drawing a picture to find that direction. I certainly can't do it without the picture because I'm not sure whether I should be adding or subtracting and how much I should be adding or subtracting to that angle alpha. So, bless you. The alpha, though, is always going to be the tan inverse of the absolute value of the x and y coordinates. So it'll always be y over x. And I'm always going to ignore the signs when I do that. Just makes life a little bit easier for me, since I have the picture. Does that feel a bit better? Soph?
Can you do 13, the negative 10 is moving out?
Sure. So it says find the component form for the vectors. Round your answers to the nearest hundredth. So my vector A is just going to be the magnitude of A times the cosine of L or theta, magnitude of A times sine of theta. So I do that, I get 2.28. And I get negative 1.02.
So, yeah, so what's happened with my calculator? Because I remember those negatives.
Yeah.
Thanks.
Yeah, of course you can turn off the light. Yeah, whenever, if you ever can't see, just feel free to just stand up and turn it off. No big deal. It just sometimes first hour it's too dark. All right, who's next on questions here? Mark. Sure. Anybody else? Colette? 19. Okay. So my unit vector in the same direction of u can be found by doing this. So the first thing I'm going to do is just calculate the magnitude of u. So that should be square root 53. So I have 1 over the square root of 53 times -2, -7. And I don't really love the form for that answer because I have the square roots in the denominator. So that's my component form answer. To write this in linear combination form, all I do is I take the x-coordinate and stick the vector I onto it, and then I write it plus the y-coordinate and stick the vector j onto the end of it. So there's my component form, and there's my linear combination form. Cool with that, Colette? Okay. Last chance on questions from this before we move on. Okie doke. So we're going to pick up where we left off in section 8.2. So in section 8.2, we've been talking about operations on vectors. So we talked about vector addition, subtraction, and scalar multiplication. Today we're going to talk about another type of vector multiplication called the dot product. Or we're going to start anyways by talking about that. So let's say we have a vector u with components u1 and u2, and a vector v with components v1 and v2. We say that the dot product of u and v is denoted u dot v, and u dot v is equal to u1 times v1 plus u2 times v2. So the notation here is kind of mean, right? Because the dot product symbol is the same as the scalar multiplication symbol. So how can you tell them apart? Okay, how they're used. So a dot product occurs between two vectors. Scalar multiplication occurs between a vector and a scalar, right? And remind me again, what do I mean when I say a scalar? It's like just a number, like a regular old real number, like 8. Everybody's okay there? Okay. What else do you notice that's a little bit odd about this dot product? What are we getting back when we take the dot product of two vectors? U1 and V1 and U2 and V2, those are just real numbers, right? We're getting back a scalar when we take the dot product of two vectors. This is the only vector operation we've seen so far where I don't get another vector back. So that's an important distinction, is that when you take the dot product of two vectors, you're not getting another vector. You're getting a scalar, just a single real number. Okay? All right. So let's look at some properties of the dot product. So here I'm going to use u, v, and w as vectors. And I'm going to use k just to be a scalar. So the first thing is we have a commutative property. And what the commutative property says is that you can do the dot product in either order. So u dot v is the same as v dot u. That's convenient. We have a multiplicative identity property. So if I do the dot product of the 0 vector and u, what do you suspect we're going to get back? If I take the dot product of the 0 vector and u, what do you suppose we're going to get? 0. Yeah. So we have a distributive property. And again, because we know that the dot product is commutative, it doesn't matter which side we're taking the dot product from. We have something called the Scalar Associative Property. What this does is it describes how to do scalar multiplication and dot products at the same time. So what that scalar associative property is saying, oops, I used k for my scalar. Says is that if I have a scalar multiplication going on with a dot product, it doesn't really matter when I do that scalar multiplication. I could scalar multiply the first vector and then take the dot product. I could scalar multiply with the second vector and then take the dot product. Or I could take the dot product and then do the scalar multiplication. It doesn't matter when I do that. I'm going to get the same result. And the last one is the magnitude property. What this says is if I take the dot product of a vector with itself, it gives me the magnitude of that vector squared. So we're going to ask that you prove these properties in the homework. So we're not going to prove them all right now. But I will do one of them right now just to give you guys like an example to kind of follow. Okay? I'm going to pick to do the fourth one because I think it's a good representative example. So what I'm going to do is I'm going to define my vectors u and v in component form. And then just pick k to be some real number. And what I want to prove here was this string of equalities. So my plan for this proof is going to be to take each part of this equality and show that each one of these three pieces is equal to the same thing. Because if they're all equal to the same thing, they all have to be equal together, right? Is everybody okay with that plan? Okay. So I'm going to start with the first one. So I'm going to just begin by replacing my vectors with their component forms. Now I'm going to just follow the order of operation and begin by doing the scalar multiplication as directed by the set of parentheses. And now I'm going to do my dot product. So it takes the product of the x coordinates plus the product of the y coordinates. And since k, u1, and v1 are all real numbers, it doesn't matter the order in which I do that multiplication, so I can just drop the parentheses. And similar for k, u2, and v2. So I just drop those parentheses. Now I'm going to do the second piece of my equality. I'm just going to do exactly the same thing. So I'm just going to replace my vectors with their component forms. I'm going to do the scalar multiplication as directed by the set of parentheses. I'm going to perform my dot product. And now since u1, k, and v1 are real numbers, it doesn't matter the order I do this multiplication. So I'm going to write it in this order. Similarly with u2, k, and v2, it doesn't matter the order I write them, so I'm going to write them in that order. Which you'll notice is the same thing that we got above in the yellow. So we have proven the first equality. There's one more equality to do, though. And just like before, I'm going to start by rewriting things into their component form. This time the parentheses indicate I should do the dot product first. And then because k, u1, v1, and u2, v2 are all real numbers, I know the distributive property holds. So I'm just going to distribute the k through. Oops. And I have, oops, exactly the same thing. So since they're all equal to the same thing, they must all be equal to each other, right? Alicia? One has a tail, the other doesn't. So let's look at a numeric example. So let's say we have the vector u, which is the vector 2, -3. Yes. Okay.
So in the second part of the vector, when you go from like u1, u2, the second line, how did you go from that to the third line? Like where did you the second to the third line?
That's me using the dot product. That's the definition. You multiply the x components together and you multiply the y components together, then you add them. So I have this times this, and then this times this. Okay, that's just how we do the dot product. That's its definition. Is you multiply the x's together and you multiply the y's together and you add those two products. Okay, sure. That's what you're asking though, right? Okay, sure. I just want to make sure before I moved on. All right, so let's look at this numeric example here. So first thing I'm going to do is I'm going to rewrite these vectors so that they're all in component form. Notice vector w we've written as a linear combination. How do I rewrite vector w so that it's in component form? The fact that one person whispered an answer is kind of concerning. How would I rewrite vector w that's in linear combination form into component form? You can answer the question while you're writing, though, right? Okay, it's really easy. It's 8, 4. All right. So I would begin by stop talking, please. Replacing the vectors with their component forms. Everybody okay there? So I'm going to follow the order of operations and do the piece in the parentheses first. So to subtract two vectors, I just subtract their components. 2 minus 8 is -6. -3 minus 4 is -7. And then I'm going to do the scalar multiplication. 2 times negative 1 is negative 2, and 2 times 5 is 10. Now I'm going to perform the dot product, so that's going to be negative 6 times negative 2 plus negative 7 times positive 10. So 12 minus 70, or 58. So not too bad, right? All we were doing was just like simple addition, subtraction, multiplications. You just had to be able to follow the directions and understand how the vector operations work. And again, if you're not sure on those sorts of things, that's what you really need to be practicing when you're doing the homework, is focusing on, okay, like understanding what the symbols mean, how the operations work, what the directions are. So the vocab and the symbols are really the hard part here. The computations that we're doing are all fairly straightforward, right? It just basically add, subtract, multiply kind of things. Not super tough. Not a lot of algebraic symbol manipulation, but you got to know how to do the operations. That was the problem in black. My work is red. Okay. All right. So one thing we can use the dot product for is calculating the angle between two vectors. So let's imagine we have two vectors. So I'm going to draw them in the xy plane here. Let's say we have vector u here, which I'm going to designate as u1, u2. And maybe I have vector v here, which I'm going to designate as v1, v2. What we're interested in here is this angle between the two vectors. Okay. So if I look at these two vectors, what shape do these two vectors resemble? A triangle. Great. So let's make a triangle here. Okay, so I'm going to draw in a third vector here to complete my triangle. The question becomes, what should the name of that vector be? This vector should be v minus u. Okay, why? So let's look at what we've drawn here. So I drew vector u, and then starting at the head of vector u is the tail of the gray vector, right? What vector operation geometrically is related to writing the vector's head to tail like this? The head minus tail was how to get things into component form. It was not a vector operation. But I understand why you would guess that, considering we're talking about heads and tails. No, it's vector addition. So u plus whatever this gray vector is should give me then my vector v, which would be my resultant. So what should the gray vector be? If I subtract the u from both sides, it should be v minus u, right? Okay. So I have these three vectors, so I know something about their magnitudes and their directions, right? The magnitudes of the vectors are the same thing as the length of the vectors. So essentially here I know something about all three sides of this triangle. Everybody okay with that idea? If I know the three sides of the triangle, and I'm interested in an angle in the triangle, how would I find that angle? You all just took a test on this quite recently. So if I know all three, what was that? Law of cosines. Very good. So what I can say is that the magnitude of v minus u squared is equal to the magnitude of v squared plus the magnitude of u squared minus 2 times the magnitude of v times the magnitude of u times the cosine of theta. Is everybody okay with that? It's just me applying the law of cosines, right? Now what I'm going to do is with this vector, or with this, actually I should say this magnitude squared, I'm going to apply the magnitude property of dot products. You go back and look at property 5, it says that the dot product of a vector with itself is equal to its magnitude squared. So I'm going to rewrite this then as v minus u dot v minus u. And then everything else is just going to stay the same. Now, since I have the distributive property, what do you suppose I can do with this dot product here? Since I have a distributive property for dot products, how can I do that dot product v minus u dot v minus u? Foil it. Exactly right. So that's going to give me v dot v minus 2 v dot u plus u dot u. And then I'm just going to keep the entire other side the same. So if I notice I have a vector dot product itself, right? Which property of vectors applies in that situation? The magnitude property. So I can rewrite those as magnitude of vector v squared Everybody okay here? What's going to happen if I subtract the magnitude of v squared from both sides? They're going to cancel. And if I subtract the magnitude of u squared from both sides? Yes, sir. Sure. And remember, we're interested in the angle between these two vectors, so I'm interested in solving for theta here, right? So now I'm just going to divide both sides by -2 magnitude of v times magnitude of u. So we notice there the -2's will reduce. And then if I just take the cosine inverse of both sides, I'm left with the formula v dot u over the magnitude of v times the magnitude of u is equal to theta.
Wait, are you serious? Yeah, but why did we have to
Just to be able to use it. It's a 7 with a comma next to it. All right. So we just developed this formula. Let's do a numeric example now. What? Yeah. All right. We're asked for the measure of the angle between two vectors. So we're going to use this formula we just developed, right? So to use this formula, I need three things. I need v dot u, I need the magnitude of v, and I need the magnitude of u, right? So let's see, 7 times 2 is 14, plus -6 times 2 is -12. So the dot product of those two vectors is 2. The magnitude of v is just the square root of 2 squared plus 2 squared, so that's the square root of 8. And the magnitude of u is v squared plus -6 squared, square rooted, so that's the square root of 85, I think. So when I plug these in, I'm just going to take the cosine inverse of 2 over the square root of 8 times the square root of 85. And now it's calculator time. So I'll just do cosine inverse of the fraction 2 over root 8 times root 85. So I get 85.60. That's the angle between those two vectors. Anj. Yeah. The definition of the dot product is we multiply the x components together, and then we add that to the y components multiplied together. The dot product formula is u1 v1 plus u2 v2. Okay. So we've been talking about finding the angle between two vectors. What do you think, or what would you say is the most important angle measure? 90 degrees, right? We're going to be of special interest in when vectors are 90, or the angle between two vectors is 90 degrees. We're going to give that a special name. We're going to call it orthogonal. It's just a name, guys. What are you? If I said this bone is called the femur, you'd be like, what? That's a weird name. It's just a name. Goodness gracious. I'm sorry that it has more than one syllable. English? So we can say that two vectors are orthogonal if and only if. That's an angle symbol. 90-degree angle between. We just said it aloud. If and only if their dot product is 0. So suppose I ask you to show that two vectors are orthogonal. What's the easiest way to do this? Yeah, just check their dot product is 0. So what do I get? That's it. They're orthogonal. You can write IFF as an abbreviation for if and only if you prefer. Yeah, I used to write that frequently, and people would be like, why are you misspelling if? And it's like, well, when I read it aloud, I said if and only if. And this is just abbreviation for it, which I know you've seen in your geometry class. They're like, oh, no, I didn't. I'm like, all right, fine. Let's just write out if and only if. All right. Okay, next up, we're going to talk about some applications of vectors. So this kind of a story problem should sound quite familiar. We dealt with these sorts of situations in first semester, right? The approach that we're going to take is not any different. We're just going to use the language of vectors here to deal with this now rather than just trigonometry. So when you read this problem, how many vectors do you hear? 2. Good. 1 for each leg of the trip, right? So I'm going to start by drawing the first vector for the first leg of our journey. So it says the boat goes on a course of 215 degrees. When we talk about courses and bearings, how do we draw those angles? You have to draw from the north. And which direction do we rotate? Clockwise. So 90, 180, 35 more is like my 215 degrees. However, that's not the angle we're interested in when doing our calculations. The angle that we want is really our standard position angle. What is that going to be? $180 plus 55, right? Where did the 55 come from? 90 minus 135, right? Is everybody okay there? So if I call this vector v, what's the magnitude of vector v in this case? Well, it's the length of that arrow. If we're going 40 miles per hour or 40 knots for 2 hours, that means we've gone 80 nautical miles. That's what a knot is a nautical mile. So we're just going to do 80 times cosine of 235 and 80 sine 235. And that's going to describe our vector v. Now you could right now take that and turn it into a decimal if you wanted to. I'm not going to do that right now. But if you wanted to, you could use your calculator and turn that into a decimal. The next leg of our trip, we have a bearing of 162 degrees. So 90 and then like 72 more. No, those should be 235s. 180 plus 55 is 235. So really interested in this angle here. What is that angle theta going to be? So 288. And if I call this vector vector u, the magnitude of u would be 3 times 55. So with the magnitude and direction, then I can write the vector in component form. Everybody okay there? So then the final position of the ship is going to be at vector u plus v. And when I type that into my calculator, I get 5.10 negative 222.46.
Why didn't you solve for the numbers before? Why did you keep going them up?
Because I didn't want to take out my calculator more than once. It doesn't really matter. You could have solved for numbers earlier. It doesn't. What are you G'ing him for? That seems unfair. Okay. So the distance then from the port is going to be the same thing as the magnitude of that vector so when I do that, I get 222.51 nautical miles. And then to get its bearing, I'm going to have to draw a picture. So when I plot this point, I'm going to go 5 over and negative 200 down. So it's going to look like that. So I'm going to start by drawing my reference triangle. And I'm interested in this angle alpha, where this side is 2246 and this side is 510. So I'll do tan inverse of opposite over adjacent. And when I do that, I get 88.69 degrees. And if I'm interested in the bearing, I'm interested in this angle. So that's going to be 90 plus that 88.69. So that's a 178.69 degrees. So there's my bearing. Notice that it asks for a bearing, so that would be different than if it asks for the position or the direction, which would be the standard position angle. Now, recall that this is not really decidedly different than what we did first semester, right? We did these problems first semester. We took almost exactly the same approach. The only difference is here I've acknowledged that these things are vectors. And used a bit of the vector notation and formula justification. We're going to stop here because the next topic is a big one that I can't do in 5 minutes, or even really get an appreciable start in 5 minutes. So we'll stop here. What I'd like for you guys to work on, though, for next time is 23 through 40.